Hello everyone, and I hope you enjoyed my last video where we discussed another version of the Atwood machine. I would suggest we go back to that video because that video is only half done. Remember, it was Atwood machine 2 version 1, part 1. This is Atwood machine 2 part 2. Please go back and look at part 1 to make more sense of this video. Part 1 ended with two simultaneous equations with three unknowns, which means we need a third simultaneous equation. Newton's law couldn't help us in that respect. So where is this third equation of motion, if indeed it exists? Well, we'll have to look at constraints here. Some things are constrained to stay the same in this apparatus. For example, look at the two masses. It doesn't matter where these two masses are in position, the height of the apparatus always stays the same. H, as you might think, well, that's obvious. It's obvious that the height is going to change. Yes, it is obvious, but sometimes in physics, even the most obvious thing has to be stated. In this case, the height of the apparatus doesn't change. An obvious statement, but it has to be made. Another thing that won't change is the length of the strings. That won't change. So the string on the upper left, that's not that B plus C, that's not going to change. And the change and the string on the lower right also won't change. So then if we make up all of these constraints equations, for example, A plus B is equal to the height, B plus C is equal to the length of the upper string on the left, and so on, for all the things we can think of, we have these list of constraint equations. And those must always hold, irrespective of where the masses are. They must always hold. So what I'm going to do is I'm going to assume that when mass m1 rises by 1 unit, mass m2 falls by 1 unit. Now, if I'm right, then we make the appropriate changes, and all the constraint equations will still hold. If I'm wrong, then they won't hold and we'll have to make an adjustment. So if we change all the positions by 1 unit, all the constraint equations hold except for the one in red. C plus E plus F is equal to the height. But C plus 1 plus E plus 1 plus F minus 1 is equal to H plus 1, which is wrong. You can't have that. It has to be equal to H. Otherwise you're getting another unit of height. So in other words, when the mass on the left rises by 1, the mass on the lower right must fall by 2. So it's not C plus 1 plus E plus 1 plus F minus 1, it is plus F minus 2 to make the constraint equation hold. And that's, you might think, well, why would that be? Well, when the pulley on the right is falling by 1 unit, the string on the right that the mass is attached to is also increasing by 1 unit. So that's a 2 unit increase. So in other words, when the mass goes up by 1 on the left, the mass goes down by 2 on the right. And that means its acceleration is twice as much. Well, why would that be? Well, imagine you've got two cars, for example, and they both start at the same bit. And they both accelerate uniformly. Car A travels a certain distance, but car B travels, say, 3 times as much. If car B is travelling 3 times as much in the same time, it's got 3 times the average speed. And if it's got 3 times the average speed, and they've both been accelerating for the same time, then it's necessarily that car B has 3 times the acceleration, and that's the argument here. Meaning that the acceleration A1 is equal to negative twice the acceleration of A2. And that's our third constraint equation. Well, there we have our two equations then for A1 and A2. And if you look at these formulas, you can see why we call this device a machine. Well, what are machines? Well, machines are there to make doing work easier. In this case, our work is moving or raising the M1 mass on the left. And if we look at these two formulas, we can see the M1 mass on the left can be directly balanced by exactly half of that mass on the right. So for example, suppose we wish to raise a 10,000 Newton mass, M1, on the left. Well, if we put a 5,000 Newton mass on the right hand side at a higher level, it's perfectly balanced. So if we come along and gently pull down on that 5,000 Newton mass on the right, that will raise the 10,000 Newton mass on the left, meaning it's half of the force is required. And similarly, if you allowed it to fall, suppose there's no friction in it and it falls uniformly, well, we'll see the right hand side falling at twice the rate of the left hand side. So in other words, every time we pull down the right hand side by 1 unit, the left hand side M1 will rise by half a unit, keeping the laws of physics correct. And this is what all machines do. We might have to work a wee bit longer, but if it makes the job a lot easier, that's fine.